In this video, we'll discuss on the topic code generation. Code generation is the last phase of the compiler. Having converted a given program into an intermediate code, the next phase is to convert the intermediate code into a set of machine language instructions or an assembly level instructions based on the processor what we are going to execute. There are certain issues which has to be looked into while we generate a code, either the assembly language or the machine language code. So first we'll discuss on those issues, and then we'll talk about the code generation algorithm and the points in which the code generation algorithm really peeps into so that the issues are being resolved. Now, what are the issues in the code generation phase? The first one is the input to the code generator. What kind of input are we really going to provide? Are we going to give the intermediate code in terms of a 3-address representation, or we are going to produce it in terms of a triple, quadruple? What type of representation is the syntax tree which is given as input to the code generator does matter. So we have to really look into what is the input for the input code generated. It's not saying that it is an intermediate code, rather it is saying what type of representation is used for the intermediate code presentation. And the next one is the target program. Target program is important because we cannot just classify into whether it's an assembly code or it is an machine language code, but we should also know to based on which processor are we really going to convert it into, and therefore target program is required because the compiler should have a knowledge of the instructions what the particular processor is using, the locations where the instructions can be stored, so on and so forth, and therefore it is must required. And the third issue is the memory management. We have to map every of the local variable, global variable into different areas. We have the static area, we have the stack, we have the heap allocation. So where are we really going to save all those variables? How many transfers are required from memory to register, and so on and so forth has to be really dealt with. So mapping of names in the source program to the address of the data object is required, which is done in pass 1. What is pass 1? Pass 1 is the front end of the compiler, that is still your intermediate code phase, and pass 2 will be code generation as such. So all these things has to be taken care of. Now the fourth point is how you select an instruction. Easy way of doing it is you try to map a single intermediate code to a sequence of instruction from your assembly language code or your machine instructions. Just for example, if you say a equal to a plus 1, first thing is or a equal to a plus b, first you move the content of a to register 1, second one is you move the content of b to register 2, and then you add the content of register 1 and register 2, and then we move back the content of a back to the memory. But then we have the system does a little bit of analysis in order to optimize the execution time. So now what are we going to do? We are just going to take a simple example and see how it works out. You have two instructions which is of 3-address code format. It is just a equal to b plus c and d equal to a plus c. Now b has to be there somewhere. So what they are doing is b is moved on to a register. You add the content of the register with the content of the memory location where c's value is stored in. Now here this instruction set allows the content of register to be added with the content of the memory. If so, we can go ahead with it. And then you try to move the content of the register content or 0. That is the sum of b and c to a. So it is moved back to the memory location. And now what you do again? Now again I need the value of a. So a's value again move back to register or 0. Then you try to add with the content e. And then you move it. Now if you see here, it seems well and good, but then your movement of a, you try to move the content of a to register from the register R0 to the memory location which is for the variable a, and then the next step itself you try to move the content of the same memory location back to an register. So these two are redundant. I can delete this one because you have some value in A, and therefore, or you say you have just moved back or not information to A, but still you will have a copy of the A's value in or not. So this instruction can be removed so that you reduce some of memory to register transfer cost. So such type of analysis is required for efficient programming, and therefore a selection of instructions and the order in which the instructions get executed plays a major role when you generate the assembly language code or the machine language code. And the next one is register allocation. Which register are we going to choose? Now in this example, you only meddle with only one register. But then we should know how many registers are really there. Which register are we going to use? Now for this example, you can always say B's content is moved on to R0. You combine, add it, it's there in R0. Now what is R0's value? It's A value. Now instead of moving A to R0 and switching it back, I can always move E's content to R1. Add R0 on R1. So R0's content is A, R1's content is A plus E, and then you can move that to and register so that you reduce certain of the movement of the data between the memory and the register. So register selection is very, very important. That is point number one. And the next issue when you do go for register selection is, suppose for example I have 4 registers. Just for example, okay. You have in register or not, let me have the value of A. B is stored in R1, C is stored in R2, and D is stored in R3. Now, I don't need the value of the register content R1, which is B, but I need the value of A. Now, I have to shift another value of variable E onto the register. Now, if I don't have a free register. So, what do? I remove some of the register content and replace it with E. So if I choose or not, where E's content can be transferred, and the next instruction tells me I need the value of A, so you have to go and transfer A's content onto R1. So you have 2 transfers. Let me do a little bit of analysis, add intelligence onto it and say I need the content of R0 for some other purpose, that is A's value for the next instruction, and therefore the next instruction doesn't require B's value. Let me not remove R0's value, but let me change R1's value, replace B's content with E's content. In that case, the number of memory to register transfer is going to be reduced. So we need to know how many transfers can happen if I choose a register content to be replaced. So all these things plays a major role when it goes for a register allocation. So register allocation is a selection process where the set of variables will reside in a different registers. What is register assignment? You can pick the register that contains a variable, say this is required for some more amount of time, and the other content in another register is not required, so you replace it. But this is an NP complete problem which cannot be completed in a polynomial time. So it requires different techniques to be adapted. So the issue is always, there are certain cases, the issue also goes with the hardware. Now they says for some instructions only these registers can be used. So you have specific registers which are allotted for some instructions, and therefore we don't have any other choice. That is number 1. Number 2, they always say, or there are software constraints saying, for example, R6 is always used for a return address. So by the time you calculate something, your return address is there in R1, you have to change it to R2, only then it acts as a return address. The same for the stack pointers. Similarly, we have registers for branching, for heap management, so on and so forth. So all these has to be taken into consideration. And the last one is the evaluation order. Now evaluation order, there can be a little bit of change. Now for example, I'll give you an easy example of how things work on. We'll just take an example and see how really things work here. We'll say A equal to A equal to B plus C, and then I'll have another instruction saying D is equal to E plus F. Okay, D is equal to E plus F, and the third instruction says what to say, okay, G is equal to A plus C. Now let me say I have only 3 registers. We'll take it as R1, R2 and R3. Now first time let me move, for example, B's content onto R1 and C's content onto R2. Now you add it and store A's content onto R1. Now I have A's content in R1, C's content in R2. Now the next step is what I am supposed to do is to say E plus F. So now what I have to do, my free register is R3. So I'll say E is stored in R3, and the next maybe I choose R1. So yeah, in R1 I put F. You do an addition, and somewhere down the lane you add D's content is there in R3. Now this is one way of doing. Now I have to again take back A. So what I'll do, I'll move A's content onto R1, then add it. Now I'll do a little bit of change here. I'll change the instruction evaluation order in a different way. Now what can be done? Instead of having D plus equal to EF as the second instruction, I'll have it as the third instruction. So now what happens? You have B's content onto register R1, C's content onto register R2, for example. Now you say you add it and put A's content onto R1. Now A content is there in R1. Now let me do a little bit of change. A's content is also there, C's content is also there. So now let me add these two and put G's content maybe here. G's content in R2 or maybe in R1. Now pulling A back to the memory and taking it back to the register content can be saved when you just look at all this. So this is how you do a little bit of change in the evaluation order. Now who does the change? It is not the programmer but the compiler which does the change. That is what is said here. You add XY and the temporary variable is T1, add AB and the temporary variable is T2. Check whether they are dependent or they are not dependent. Sometimes A's value will be affected. Now how will we do all this? We'll do as analysis, data flow analysis, which comes in the optimization part, which we'll be seeing in the next video. So you have a little bit of data analysis, check which variables are affected by the other variable, and then make a clear analysis of how the evaluation order has to be. So this is one of the other issue which we have to take care of. Now these are the 6 issues for a code generator. Moving on, we'll go on for the code generation algorithm. So the code generation algorithm, the first step is to identify the next use information. What is that next use information? Whenever you define a variable, those variables are evaluated and the values are stored in the register. You have to identify when those register contents will be used next. So that is what they have said here. In the ith instruction, they have used X, Y and Z. And in between, I don't have any assignment of this value X. And only in the jth instruction, I am going to use X. So this is a data flow analysis which the compiler makes and which you call it as the next use information. So based on it, we know whether you have to retain the content in the register or we can replace it for bringing in some other values. And once that is done, we generate a set of basic blocks. Now all these has to be done based on the basic block information. We'll see how this basic blocks will be splitted up in the next video. So we have in the program, we try to group it into small blocks, and we ensure for every block you have a set of registers and you try to allocate registers based on it. So when you take a single basic block, you have a register descriptor, you have a get register function which tries to get the required registers based on the next use information and assign registers for evaluating the expressions what is given in the program. If the the required variable, suppose you have y and z which is required to evaluate the value x. If y's content is already there and z content is already there, then there is no requirement for a load instruction. Those content is not there in the register, then a load instruction is required. At that particular point of time, we try to identify a register and then load the content of x, y and z onto that particular register. And the last one is if you have a copy information. If you have a copy information, now you have to check whether the register content R0 contains the value y. If it contains the value y, now the x can also point on to it. If that is not the case, then you have to select a register for both x and y. A single register has to be selected so that you place the content onto it. Now, once all is done, once this has been executed, now I have to store the information which is in register which contains the y value which we have now assigned it to x onto x memory location. So you have a store instruction which gets generated. So if there are no empty registers, then what are we supposed to do? We are supposed to find out a register which has the value which can be used in a very later position, or has a value which will not be used further in your program. In that case, those register content can be replaced by the required one, which is being how do I select the register? That is based on the heuristic technique which we have. With this, we come to an end of the code generation algorithm. Thank you.